Yes, thank you so much. Just let me start the timing so I don't go over so much. So thank you for the invitation. I'm going to talk about ZNL Energy and the next generation separator called ZNL-NPX. So there's a problem ready to be solved when it comes to batteries. It's poor fire safety, it's low lifetime expectancy, and of course, low energy density. So modifying two parameters is relatively straightforward for cell makers. However, adjusting parameters involve trade-offs between cycle life, fire safety, and of course, energy density. So the ZNL NPX is tackling this compromise head-on. It's important to understand that we are a drop-in replacement, meaning you don't have to re-engineer your factory or your battery cells to use our products. We are doubling useful lifetime because of the way the separator is produced, and we have enabling higher energy density, and of course, we eliminate fire. So the market at a glance, the McKinsey report says the largest battery value chain white space in Europe and US because there's only 3% of all separators manufactured in the world today comes from Europe or US. So when you have battery projects going on in Europe and US, one of the key components, it's still bought either from China, Japan, or Korea. So home sourcing and geopolitical thing can be an issue if you want to home. And the Industrial Accelerator Act that just came showcase that you need key components in Europe. So what's the difference between the conventional separator and ours? The conventional separators are porous, meaning they transport the ions through microporous structures and electrolytes. Ours is a PPS, it's non-porous, meaning it transports the ions through something called diffusion. There's a crystalline structure inside the PPS where the ions transport, and only the ions that you want to transport, even if it's lithium ions, sodium ions, or zinc ions. We also have a PE layers on the anode side. If you have a thermal event, that will shrink, but the integrity of the separator will withhold because of the high melting point and the shrinkage that we have on the PPS. You don't expose the electrodes. What happens in conventional separator when there's a temperature event, it will melt and you expose the electrodes. We also did an exciting internal test where we took iron powder on a NMC 811 cell on the cathode to simulate what happens during contamination. The conventional separator battery cell couldn't even take a charge. It just short circuited at once. With our separator, it just kept no worries and it went completely fine. We also have external tests. This is from a sodium with 4 voltage. And you see the orange and the scattered, it's the conventional separator. With ours is almost at 100%, and it's really even on the cycling. So we lasted over 900 cycles. So this is on the next level chemistry. We also see similar test in high NMC 9XX from a US player where we doubled the lifetime of the battery. So we're in positions. We are a separator producer, so we are right before cell assembly and cell production. We make advanced polymer-based separators. We are not a battery cell or a systems provider. We offer safety, durability, and longevity, and the team is based in Norway. Thank you.
Right. So, Jan, thank you very much. Very elaborating and inspiring. First critical question is, why saving energy density? Because this is a passive component in terms of energy storage. Can you elaborate on that?
Yes, so basically, if you want higher nickel in a high nickel NMC, the higher the nickel content you have, then you will have a nickel shuttling or manganese migration from one side. So you're poisoning the battery. Since we are non-porous and tight, you don't have that nickel shuttling effect or the migration of the manganese. So you can have, because the goal is in an NMC is to have as low as possible on the cobalt side because of the ethical part and the mines in Congo, and of course the manganese. Same with lithium sulfur. So we are enabling the battery cell manufacturers to have higher nickel or lithium sulfur or high voltage on sodium.
Okay, gotcha. And second question to you would be on the business case. I mean, and I learned during my visit already that this is a really high potential technology that you have there. The question is, what is the market application that you look at? Who are your customers? Because likely the innovation also comes at a price point, or?
Yes, we of course you can have the best product, but you price yourself out. Nobody wants to buy it. Right now, I developed something called a test agreement. We are right now at 40 plus test agreements with different type of OEMs, battery cell manufacturers from Europe. We actually have a European player that just did the industrial powered cells and have ordered product for the A cell level cell. And we have American-based OEM that has been testing with really, really good results. So the price point that we are looking at is the same as in the EV. So also, if you have CellGuard's high quality separator, we are competitive on the price on that. Our goal is basically to set up a separator factory to manufacture separators to either Europe or US.
Okay, so you have an ideology, not ideology, but you have a focus on the market sector. Okay, gotcha.
Yes.
All right. So Dominic, you have a question, right?
Yes, thank you for the really interesting presentation. You mentioned that you eliminate fire. Could you expand a little bit on that? Because that's a big claim.
Yes, you can actually look at a LinkedIn video that I have with 8650 cell that Tesla used to use. We penetrated that with a spike and no fire. Basically, what happened is, if you look at this slide, you see when you get the thermal event, see, for instance, dendrite formation or a thermal event, because of the PE or the PP melts down and shuts the ions. So we see on test that we go up to 8 degrees where the glass transition or the melting points of the PE and stops the ion. So it goes up to 80 and then it just drops. So you don't get the uncontrollable thermal events.